Thank you. Okay, so now I want to do some Keller geometry. And give a proof of the result of Gromov, so Gromov's upper bound for the topological entropy. Okay, so I start with Keller forms. Okay. So I want to define what a Keller form is and why it is related to Riemannian geometry and how we can use it to compute volumes or distances. So that's what I want to do. Okay, so let me start with an example, which is the most basic example. So I hope I will do it correctly. But let me define kappa. So it will be a differential form of degree 2 on C using complex coordinates. So I over 2 dz wedge dz bar. Okay, so z is a complex coordinate in C. I is just square root of -1. And what is dz? So z is x plus iy. X and y are the real and imaginary part of z. So if I expand this definition, what do I get? I get I over 2. So you see, over 2 is very important. So it's dx plus I dy. This is dz times dx minus I y. And then I continue. Okay, so I know that some people never saw what a differential, a Keller form is, so you need to do at least this computation at least once. Okay, so I do it. So dx wedge dx is 0, because I multiply the same one form, 0. dx times minus I dy, so it's minus I dx wedge dy. And I dy wedge dx is I times dy is wedge dx, and dy dx is minus dx dy. So it's minus 2 times I dx dy, and again dy is 0. And so this is why I chose I and over 2, because I times minus I is 1, and 2 divided by 2 is 1. Okay? So this form written in complex coordinates, in fact, is the same as the usual area form on R2. Okay? Okay, so that's the first remark. Second remark is, what happens if I want to evaluate kappa on a vector u, and the same vector, but which I rotate by 90 degrees. Okay, so rotating u is multiplying u by I, right? So this, let me draw a picture. U is a tangent vector, and then I multiply u by I, so this is I u. Okay, so I want to compute the value of this differential form on these two vectors. But this differential form is just the usual area form. Okay, so this value is just the area of this square. Okay, so it's the square of the modulus of u. Right? So this is the way, this is one way, I mean, the best way to relate a form like that, so a form of type 1, to a Hermitian metric, to just evaluate your 1 form on u, comma, I times u. Okay. Okay, so now if I do the same example but with n variables, let's say d variables, so I over 2, sum, so from j equal 1 to d, dzj bar. Okay. Then I get the fact that kappa of u, y over u, y times u is sum of the coordinate of u square, or modulus square. And so it's the Euclidean, or if you prefer, Hermitian norm of u to the square. Okay, so this was an example. Now I can make a definition. So let X be a complex manifold. A Keller form kappa on X is what? Is smooth, a form of type 1. So which means that locally in coordinates, I can write kappa as sum aij of z, dzi with wedge dzj bar. So there is one holomorphic and one anti-holomorphic term. So for ij less than the dimension of x, and these coefficients are smooth functions with value into C. Okay? So that's being a smooth 1 form of type 1, such that, okay, I will put 3 conditions. In fact, there is some kind of redundancy in these definitions, but I want kappa to be real. By this I mean kappa is equal to kappa bar. If I take complex conjugate, I have the same form. Second thing, I want kappa to define a Riemannian metric by the following formula. If u is a tangent vector at a point z in X, then when I compute kappa of u, comma, I times u, this defines a Riemannian metric. So for every point in X, I look at the tangent space, the complex tangent space. I take any tangent vector, and I compute this, and I want it to be, you see it's a quadratic form in U, and I want this quadratic form to be positive definite. Okay, so the condition is that this is always positive, except if U is 0. And the third condition is the fact that kappa is closed. Okay, so its differential, d kappa, is 0. D here is not the dimension, it's the differential of kappa. So these are the constraints you put on your form to get a Keller form. Okay, so here I did not insist on that, but you see dx dy is a top form on R2, so it's closed. Okay, so examples. So I will denote this by, let's say, kappa Euclidean, because when you compute the Riemannian metric here, what you get is a standard Euclidean norm. Okay. So this is an example of a Kähler form. Okay, so I'm mixing things. Okay. You see, I'm mixing the indices M and D. Let's put M here. So then it's on CM, okay? And this form, you see, when I write the formula, the coefficient here, I didn't put any coefficients. The coefficients are 1, okay? So, or 0 if I is not equal to j. Okay, so this form is invariant under translation. Okay, and since it's invariant under translation, I can induce this form when I take a quotient of Cm by a lattice. So if I take Cm and I divide by a lattice lambda, then I get a Kähler manifold. So it's a compact Kähler manifold. Okay, the second example is the Fubini-Studi metric. Okay, what I'm saying is that, so I denote by, let's say, Cm plus 1 to Pm. So it's Cm plus 1 minus 0 to Pm, the projection that you get when you construct the projective space. Then what I'm saying is that there is a unique Kähler form kappa index Fs. Fs is for Fubini-Studi on Pm, complex projective space, such that when I pull back this form by pi to get a form on Cm plus 1, the formula is the following. So it's okay, so it's 1 divided by 2 pi I, dd bar, log of what? Log of the modulus, I mean the Euclidean norm of z squared. Okay, so that's Euclidean norm in Em plus 1. Okay, so I will not define dd bar, but I mean, when you take the derivative, the d derivative, you derive with respect to the z variable. When you take d bar derivative, you derive with respect to the z bar variables. Okay, so d is sum for all variables of d over dzj dz. Okay, and so if you take a slice of Cm plus 1 by a hyperplane by saying, for instance, that the first coordinate is 1, then pi restricts to this hyperplane, to this affine hyperplane as, I mean, it restricts to a one-to-one map onto its image, and in these coordinates, so in coordinates, affine coordinates, say 1, W1, W2, Wm, you can compute this thing, and you get some kind of horrible formula. It's what? It's 1 over pi. Something like that. 1 plus. Okay, so you can write explicit formulas. Okay. Mm-hmm. That's a pullback of the Fubini 2D metric restricted to the W coordinate. You know, is it good? And I hope I didn't make any mistake. In fact, in my notes, I wrote this. So maybe I'm making a mistake on the blackboard, okay. And the mistake will, I mean, if I put I above or below, I change the sign by -1. So it's a matter of being positive definite or negative definite, and I want it to be positive definite. So I should, given this, I should put the I here. Okay. Okay, so that's how you define it using formulas. In fact, what is important, up to a positive scalar multiple, it is the only Keller form on the M, which is invariant under the linear projective action of the unitary group. It's even better than that. If you look for a 1-1 form on PM, which is non-zero and invariant under the unitary group, then it is the Fubini 2D metric up to some scalar factor. And so if you choose the scalar factor to be positive, you get a Keller form, and that's it. Okay. So you see, this means that the projective space is a compact Keller manifold. And now if you take a projective manifold, a complex projective manifold, you can embed your manifold in PM. So X projective manifold over C. So you embed in some Pn. And then you take the Fubini 2D metric of Pn and you restrict it to X. And this is a Keller form on X. Okay, because the properties are invariant under restriction. Being closed is invariant if you restrict to something contained in Pn. Being positive definite is also invariant under restriction. So if you have a complex submanifold of a Keller manifold, then it is automatically Keller. Okay, so you inherit this property by being a submanifold. Okay, so I guess what is important for this week is that projective manifolds are compact Keller manifolds. Okay. So again, let me come back to the definition. If I have a compact Keller manifold, I can choose a Keller form on the manifold. Then I can define, using this formula, a Riemannian metric on my manifold, viewed as a real manifold now. And so I can talk about length, volume, distances, things like that. Okay, so the distance between 2 points is you draw a smooth path between the 2 points, and you integrate the speed of the vector, the speed of the curve. You get a number, which is the length of this path, and then you minimize above, taking all possible paths from x to y. This is your distance. Okay, so the important thing is that we can compute, the first important thing is that we can compute volumes in the sense of Riemannian geometry using the Kähler form. Okay. What I say is the following. Okay, so I will consider a submanifold of X, and X is, let's say, Kähler with a Kähler form kappa. Here, by a submanifold, I take any real submanifold, just submanifold in the sense of differential geometry, and I will assume, say, it's oriented. Okay, and of dimension 2R. So I want the dimension to be even. Then I have the following inequality. I can integrate on V my differential form kappa to the R. So this is just kappa, which kappa R times, and divide by factorial R. And then this is bounded from above by the volume of V, of course, the volume in dimension 2R, with respect to the Riemannian metric. Associated to kappa. Okay? I don't write it, but it's a Riemannian metric determined by kappa. So that's the inequality. And moreover, there is equality if and only if V is a complex submanifold with its canonical orientation. So what is the canonical orientation? You know, if you have in complex geometry, you have charts into C to the M, where M is a dimension. Changes of charts are holomorphic maps. Okay, so their Jacobian determinant in the sense of real geometry is the square of the modulus of the Jacobian determinant in the sense of complex analysis. Okay, so it's always positive. So if I put the usual orientation on C to the M, I get an orientation on my manifold. Another way to say it, if you take a point in your manifold and you take a basis of the tangent space, the complex tangent space, so you get M vectors, each of the elements in your basis, you can rotate it by 90 degrees by multiplication by I, square root of -1. Okay, and you get a new basis, but of the real tangent space, so it's U1, square root of -1 times U1, etc. And this, by definition, is positively oriented. Okay, so that's the theorem. So I write it, okay. So this is the volume of V if V is a complex submanifold. So now if X is compact Kähler and V is a submanifold of this compact Kähler manifold, then I can take the class of V in homology, and I can take the class of kappa in cohomology because kappa is closed. And this integral is just a product between cohomology and homology. Okay, so this is just the fundamental class of V, which is canonically oriented, intersected with the class of kappa to the R. Okay, and then I have to divide by this factorial. Okay, so this here is in the homology group, and this class kappa is in H2 of X with real coefficients. Okay, with the Dolbeault homology group, it's H11. Okay, and kappa to the R is the same as, let's say by definition, as the class of kappa to the R is in HPP. Okay, so let's comment a little bit these formulas. You see, you start with a complex submanifold. Thank you. These are. Right? Thank you. Let me make a comment. Suppose you start with a complex submanifold and you look at this formula, and then you deform a little bit your complex manifold V as a real manifold, you know? You just deform it like in C1 topology, you know? Then the volume can increase because of this formula, but cannot decrease because of this formula. Okay? So it's very important, you see, in Kähler geometry, first, volumes of global objects can be computed using homology cohomology. And secondly, complex submanifolds are minimal in the sense of Riemannian geometry. Okay? Somehow they minimize the Riemannian complexity given the homology class. Okay? If you perturb them a little bit, what can happen is that the volume increases, but it cannot decrease. Okay? So you know, it's like when you have a curve, you can in a surface, you can try to straight the curve to get a geodesic. Okay? In Kähler geometry, it's automatically the tightest, straightest submanifold that you can get because of this equality and this inequality. Okay? Okay, so let me write it. Okay. Complex submanifold are minimal for the volume in the sense of Riemannian geometry. Okay. Okay, and to explain it quickly, I was mixing two settings. I mean, this type of formula is local formula. You can do this type of computation locally on some open set of your manifold. Okay. This type of equality is like a global formula. Okay. The fact that it is minimal in the sense of Riemannian geometry is both local and global. Okay. Like that. Okay, so now I want to, yes? Okay, so again, I'm mixing two things. This is just Hermitian geometry. I don't need kappa to be closed. Here, I need kappa to be closed. Okay? Because otherwise, I cannot say I take the cohomology class of my closed form. Is that good? Okay, and what I didn't say, maybe I write it here, or here, for the Fubini-Studi metric and V in Pm of dimension R over C. So I take a complex submanifold of Pm. I can apply this equality. So the volume of V for the Fubini-Studi metric is equal to the class of V intersected with the class of the Fubini-Studi metric, the R. And what you get, in fact, is the degree of V. So the degree of V has a subvariety of Pm, which is V intersected with a hyperplane section to the R. So H is a hyperplane. Okay, this is intersection product. Okay. So you can think about it as topological intersection product or as the intersection product which has been used last week and this week. But then I have to say that V is algebraic, which is automatic. Okay. Okay, so this was the first important tool from Keller geometry. Now I want to come back to the definition of dynamical degrees. And then I will start the proof of Gromov's upper bound theorem. So dynamical degrees of endomorphisms. Okay, not, at least at the beginning, I don't want to look at dynamical degrees of rational transformations. I want to look at dynamical degrees of endomorphisms. So I insist regular endomorphisms. Okay, and here I will work in the setting of Keller geometry, at least at the beginning. So an endomorphism of a compact Keller manifold is just a holomorphic transformation of this compact Keller manifold. Okay, so let me recall that we have these groups HPP of X with real coefficients, which is part of the cohomology group of degree 2p. And now if I start with an endomorphism F, I have an action of F star on this group. Okay. If I want to remind me that this action is at the level of the HPP group, I might write an index P here. And what we defined is lambda of F in degree P, or codimension P, is the spectral radius of F star on HPP. Okay, this is the definition I took, and I want to compare it to the definition that Charles Favre was using last week. So that's the first thing that I want to do. The second thing I want to explain is some nice geometry in these cohomology groups. So let me start with H11. Okay, I say that H11 contains a cone, which I denote like that. The Keller cone of X. What is it? It is the cone of all classes of Keller forms. So I'm assuming that X is compact Keller, so there is at least one Keller form, and then I can take the class of this Keller form, I get an element in this cone. Okay. So it's obviously a convex cone, because if I take a Keller form, I multiply by some positive number, I get a Keller form. If I take the sum of two Keller forms, I get a Keller form. Okay. Being closed and being positive is invariant under these operations. So this is a cone. It's a convex cone. It's open because if you take a Keller form and you perturb it a little bit among closed form, being positive everywhere is stable by small perturbation. Okay? Because on a compact manifold, if something is positive, it's uniformly positive. So if you perturb a little bit, it is still positive. Okay? So it's an open convex cone. And it is salient because being positive is completely opposite to being negative. Okay, so you can prove it as an exercise. Okay, so it's an open, salient, convex cone. And this cone, or more precisely, its closure is invariant under the action of endomorphisms. Because if you take a Keller form and you pull back by an endomorphism, again you get a closed form. Again it's positive, but maybe it vanishes when the endomorphism is not a local isomorphism, okay? A local diffeomorphism. But if you perturb a little bit by adding a small Keller form, then you end up in the Keller cone. Okay, so this closure is invariant under F star. Okay, so we are in a situation where F star on H11 is a linear map preserving a salient closed convex cone whose interior is not empty. Okay. And the same is true for HPP. Define positivity by saying that the form, so you define positivity at the level of forms, and then you get something at the level of classes, that the form, let's say, omega of by degree PP is positive or non-negative if omega restricted to any so I need to be careful, p-dimensional local complex submanifold V in X, okay, of complex dimension P. So you started with a PP form on something which is X, which has dimension M. But now you restrict to something of dimension P. So you get a PP form on something of complex dimension P. So it's a top form. It's a volume form. You want it to be compatible with the canonical orientation of V. So when you evaluate this form onto the basis I described earlier that describes the orientation of V, you need to get a positive or non-negative number. Okay, so that's my definition of positivity. And then what you get is that classes of positive forms, of closed positive forms, positive I should write non-negative, okay? Positive forms form a salient closed convex cone in HPP XR. This cone contains kappa to the P in its interior for any Keller form. Okay, so first, its interior is not empty, so the cone generates HPP, and second, this is an example of a point in the interior, and second, it is invariant under F. So F star acting on HPP. Okay. So you see, at each level of the cohomology, so for each HPP, we have a natural invariant cone, the interior of which is not empty. And as an example in the interior, I just take the power of kappa. Okay, now there is this famous Perron-Frobenius theorem. Okay, that I guess you probably know. Let me state the theorem. So let W be a finite dimensional real vector space. Okay, let C in W an open cone. I take an open convex cone, or maybe I should write it like that. A closed salient convex cone with a non-empty interior. Okay, so this is the interior of C and it's not empty. Now, if F from W to W is linear and preserves C, so in the sense that F of C is contained in C. So from that, we get the following. For any vector U in the interior of C, the spectral radius of F is equal to the limit as n goes to infinity of Fn of U, take the norm, take the nth root. Okay, so for any norm on V, on W, sorry. Okay, so let me comment on that. If you have a linear transformation of a vector space, so you put a norm on the vector space, you can look at the spectral radius. So the spectral radius is the limit of the norm of f as an operator iterated n times, and you take the nth root. Okay? So to compute this, you need to look at all vectors of, let's say, of norm 1 here. When you compute the limit on the right, you are just looking at what happens for one vector. But you get the same result if there is an invariant cone and the cone contains some vector u in its interior. Okay, so that's the theorem. So maybe the version you might know is if you have a matrix with positive coefficients, okay, then its spectral radius its spectral radius is an eigenvalue, and this eigenvalue is represented by an eigenvector which has positive coordinates. This is a version of this Perron-Frobenius. I mean, this is the initial version of Perron-Frobenius theorem. Because this version is due to Birkhoff. Yeah. Is the statement clear? It's basic linear algebra, in fact. Salient. Salient means that there is a hyperplane such that the cone is completely contained on one side of the hyperplane. Okay? Or if you prefer, there is no line, a vector subspace of dimension 1, which is entirely contained in the closure of C. Okay? So I can apply this theorem to F star acting on HPP with the cone C, which is this positive cone I defined here. Okay. And then what I get is that lambda of F acting on HPP, which is the spectral radius of F star on HPP, is equal to the limit as n goes to infinity of what? Fn star applied to kappa to the p, and you take the norm in HPP, and you take the nth root. So to compute this spectral radius, you just have to look at what happens on the Kähler forms. And their Pth power. Okay? And then there is a second remark. Okay, so the remark is what? Is what I can do is the following. I take U, a class in HPP, and I map it to the following thing. I intersect U with kappa to the m minus p. So m is the dimension of x. Okay, so I'm thinking, I write it for classes, but what I'm thinking of PP forms, which I multiply and integrate over x. Okay, or if you prefer, it's just an intersection product. Okay, but here between a PP form and a m minus p form, or class. And this, you see this product, in fact, is positive on the positive cone. This means the following. So I can draw HPP. I have a cone here. So I draw a round cone, but it's typically something with a fractal boundary. So. Okay, so that's the positive cone. Okay. And here I defined a linear form, let's say, let me call it L associated to kappa, to the m minus p. So this linear form, it's just a linear form, so it has a kernel, and this kernel is a hyperplane, because it's a non-zero linear form. Okay. And the hyperplane is like that. So the positive cone is on one side of the hyperplane, and this linear form takes only positive value on this positive cone. Okay, exactly like this. So this is a closed positive cone. And now if you have such a linear form on a positive cone, you can compare the value of the linear form to the norm of a vector. And it's comparable. So there is no Keller geometry or algebraic geometry here. It's just linear algebra, okay? Then what I say is that if I integrate like that, so I apply this linear form, this is bounded from above by the norm of U, just because it's a linear form, so it's continuous, linear continuous by some multiplicative constant, but it's also bounded from below by this for every U in the positive cone. Okay, so there exists A larger than 1, such that we have that. Computing norms or computing intersection products is comparable. And then I can plug this inequality in this formula over there. Okay? And what I get is that this limit is just the limit as n goes to infinity of integral over x fn star of kappa to the p, wedge kappa to the m minus p, power 1 over n. Okay? And then I will continue below. So now I will write this formula again, assuming that x is in some projective space, and kappa is just the Fubini-Study metric. As I explained, in that case, you can replace kappa by hyperplane sections, by hyperplanes in Pn. Okay, so hyperplane sections of x. And so H is a hyperplane section. So kappa is Fubini-Study on Pn restricted to x. H is hyperplane section, let's say Hx is H intersected with x. And then what you get is limit Fn star of Hx to the p. So you take it p times, intersected Hx intersected m minus p 1 over n. Okay, so this is exactly the type of intersection using only divisors that Charles was using. Do you have a question, Michel? That's okay. Okay, so these 3 points of view are the same. Okay, so my definition of a dynamical degree using spectral radii is the same as the one using just one ample divisor H. Okay. But I think this is much better to start with the first definition, because I mean, the one using spectral radius, because you see you want to control what happens on HPP, the whole PP group. And at the end, it suffices to control what happens on a hyperplane section. Okay. So now I want to start the proof of Gromov's theorem. Okay, so I will yes. I just have 5 minutes. So okay. Instead of starting the proof, so I wanted to start the proof and then to explain something that is a consequence of minimality and how it is used in the proof. But what I will do is I will stay with scalar geometry and do the proof tomorrow. And so I will conclude with just one result, which uses the fact that complex submanifolds are minimal. Okay, so it's okay. Minimality and the monotonicity formula. So here I will do it for, let's say it will be local. So here is C to the M, the origin. I take some large ball of some radius R. And inside my ball, I take V in Cm. I mean, not in Cm, but in my ball, complex submanifold of dimension R, complex dimension R. Okay. And then what I do is the following. So for T positive but small, I look at the ball of radius T for the Euclidean metric in Cm. So this is the ball of radius T. I intersect my ball with V, and I compute a volume of this. Okay, so I look at the function T goes to volume of V intersected with the ball of radius T. Okay. So obviously, it's an increasing function. But then I can renormalize. I divide by T to the 2R. So this is a R. And what I say is that this function is increasing. In fact, we have the following formula. So 1 over T to the 2R. So here it's a 2R dimensional volume. Volume of V intersected with this ball is equal to what? It's equal to the integral of the Fubini-Studi metric on V. So it's integral on V intersected with the ball of radius T, pullback of the Fubini-Studi metric on P, M, and pi to the R factorial R. But here in this formula, I'm cheating a little bit. Because the Fubini-Study metric is on PM. When I pull back by pi, implicitly I'm working on Cm plus 1 minus the origin. Okay, let me write it like that. So what I want to say, what I'm writing here is the pullback of the Fubini-Study metric. Okay? Forget about pi. Or, yes, it's Cm or Cm plus 1. Okay, so let's say Cm to P m minus 1 was my pi. Okay? You pull back the Fubini-Study metric, you put it here, and you integrate. But let me write it in formulas. So it's I over 2 pi d bar log of z square. And here you have to take the rth power. Yeah. Okay, so let me do 2 comments. The first one is, what do you see? When you look at how this function increases, so first this is monotone. Okay, because you intersect something which is positive, non-negative, on larger and larger sets. So here this is monotonic. And this is increasing. So the same is true for that one. Okay? This was increasing, but now when I divide by t, this is not obvious. Okay? And this becomes obvious from this formula. Second thing I say is that the limit here, when t goes to 0, you know what it is. It's the volume of the ball of radius 1 in dimension r. Asymptotically, because V is smooth, when t is very, very small, locally V is like a flat space of dimension r. So this volume is like the radius t to the 2r times the volume of the ball of radius 1. Okay, so the limit is a positive number, and this is this number. Okay? So here on the right, there is something subtle happening, is that, you see, this form is not smooth at the origin. When you integrate dd bar of log of z, there is a singularity at the origin which contributes with this value. Okay, I will stop here. I think it's time. You're the chairman, yes. Yes, it is. And so what I will use tomorrow is the fact that this is monotonic and converges to a positive number. In fact, this monotonicity formula, so you can prove it by complex analysis, but it holds in the Euclidean space, real Euclidean space, just using that V is minimal. Okay, and the proof is quite simple. You can maybe sketch it later. Okay, I stop. Thank you.